Have you ever looked at a cloud and noticed how its bumpy edges look like smaller clouds? Or how a jagged coastline seems to have the same roughness no matter how closely you zoom in? For a long time, mathematics struggled to describe these kinds of shapes. Traditional geometry gave us perfect circles, squares, and triangles. But the real world is messy. It's filled with irregular, crinkly, and chaotic patterns. This is where a brilliant mathematician named Benoit Mandelbrot enters the story. He was a true maverick, someone who looked at what others dismissed as noise and saw a hidden order, a new kind of geometry. Mandelbrot was born in Poland in 1924 and later worked at IBM. He was a curious thinker who was not afraid to cross the boundaries between different fields of knowledge. He studied things that other mathematicians often ignored, like the patterns in cotton prices, the flooding of the Nile River, and the errors on telephone lines. He noticed a strange similarity in all of them, a theme of self-repetition, where the small parts of an object looked a lot like the whole object. This idea was not entirely new, but Mandelbrot was the one who gave it a name and a powerful mathematical foundation. His work was revolutionary because it offered a way to measure and understand the roughness of the natural world. He called this new branch of mathematics fractal geometry. The word fractal comes from the Latin word fractus, which means broken or fractured. This name is perfect because fractals describe the fragmented and irregular shapes we see everywhere around us. Mandelbrot showed us that complexity and chaos were not just random noise. Instead, they followed their own surprising and beautiful rules, a secret language that nature uses to build itself. This new perspective changed everything. Before Mandelbrot, a cloud was just a cloud and a mountain was just a mountain. They were too complex for simple equations. But with fractals, we gained a new lens to view our universe. We could finally see the elegant mathematical principles behind the seemingly random shapes of ferns, snowflakes, and even the branching of our own blood vessels. He didn't just invent a new type of math, he revealed a fundamental aspect of reality that had been hiding in plain sight all along. His work connected the abstract world of numbers to the tangible beauty of the world we live in. So, what exactly is a fractal? Imagine a tree. It has a main trunk that splits into large branches. Those large branches then split into smaller branches. And those smaller branches split into even smaller twigs. If you were to take a picture of a small branch and compare it to a picture of the whole tree, you would see a striking similarity in the pattern. This property is called self-similarity. It's the core idea behind fractals. A fractal is a pattern that repeats itself at different scales. No matter how much you magnify it, you keep finding smaller versions of the larger shape. Nature is the ultimate fractal artist. It uses this principle of self-similarity everywhere. Think about a snowflake. Each of its 6 arms is a miniature version of the entire snowflake's design, with smaller arms branching off in the same way. Look at a head of broccoli or cauliflower. A small floret broken off from the head looks almost identical to the whole thing, just smaller. This is not a coincidence, this is nature being efficient. Using a simple repeating rule allows it to create incredibly complex and detailed structures from a very basic set of instructions. Another fantastic example is a coastline. If you look at the coast of Britain from a satellite, it looks jagged. If you then zoom in on a single bay, that stretch of coast also looks jagged. If you were to walk along the beach and look at the edge of the water, that line would also be jagged. Mandelbrot famously asked, "How long is the coast of Britain?" The surprising answer is that it depends on the length of your ruler. The smaller the ruler you use, the more nooks and crannies you can measure and the longer the coastline becomes. A fractal shape has an infinitely long perimeter packed into a finite area. This idea of infinite detail is what makes fractals so mind-bending and beautiful. Unlike a smooth circle, which becomes a straight line if you zoom in far enough, a fractal never simplifies. It holds onto its complexity at every level of magnification. This endless repetition is not just for looks, it serves a purpose. In our lungs, the branching fractal pattern of our airways maximizes the surface area for absorbing oxygen. In a river delta, it allows water to find the most efficient path to the sea. Fractals are nature's secret blueprint for building the intricate world around us. Now, how do we get from this idea of natural patterns to the famous Mandelbrot set? The Mandelbrot set is a specific, very special fractal. It's not found in nature directly. Instead, it is born from a surprisingly simple mathematical formula. Think of it as a mathematical recipe. The recipe involves taking a number, doing a simple calculation with it, and then feeding the result back into the same calculation over and over again. This process is called iteration. The formula is very basic. You take a number, square it, and then add the original number. You then take the answer and repeat the process. The Mandelbrot set is essentially a map. It shows us which starting numbers, when put through this iterative process, behave in a certain way. The rule is simple. If the result of the repeated calculation stays small and never flies off toward infinity, then the original starting number is part of the Mandelbrot set. If the result grows bigger and bigger, escaping to infinity, then the number is not in the set. To create the famous image, a computer tests millions of numbers on a grid. It then colors each point on the grid based on whether its corresponding number belongs to the set or not. Points that are inside the set are traditionally colored black. This forms the main, bug-like shape you see in the images. But what about the points outside the set? This is where the magic really happens. For the numbers that do escape to infinity, we can color them based on how fast they escape. Numbers that grow very quickly might be colored dark blue. Numbers that take a little longer to escape might be colored light blue, then yellow, then red. This coloring method is what creates the spectacular psychedelic halos of color that surround the black shape. The most astonishing thing is what happens when you zoom into the edge of the Mandelbrot set. The boundary between the inside and the outside is where the infinite complexity lives. As you magnify this border, you don't get a smooth line. Instead, you find more and more intricate patterns. You see swirls, tendrils, and even tiny distorted copies of the entire Mandelbrot set itself, repeating forever. A simple formula, when repeated, gives rise to a universe of endless detail. It's a stunning example of how very simple rules can generate structures of unbelievable complexity. When the first images of the Mandelbrot set were generated by computers in the late 1970s and early 1980s, they caused a sensation. For the first time, people could see what these abstract mathematical equations were actually describing. The images were not just interesting, they were breathtakingly beautiful. Artists and designers were immediately drawn to their organic yet alien forms. The Mandelbrot set and other fractals became a new source of inspiration, leading to a whole new genre of digital art. The vibrant colors and infinite detail offered a visual playground unlike anything seen before. But the importance of the Mandelbrot set goes far beyond pretty pictures. It has become a vital tool in many fields of science and technology. In physics, fractal geometry helps describe chaotic systems, like the turbulence of flowing water or the weather. In biology, it is used to model the growth of tumors or the branching patterns of neurons in the brain. Computer graphics designers use fractal algorithms to create realistic-looking landscapes for movies and video games. Mountains, clouds, and trees that look natural are often generated using the same principles of self-similarity. The discovery also had a profound impact on how we think about mathematics itself. It showed that the world of numbers was not just a place of cold, rigid logic, but also a source of endless beauty and surprise. It bridged the gap between the two cultures of art and science, proving that an equation could be as awe-inspiring as a great painting. The Mandelbrot set is a universal object. Its shape is not an invention but a discovery. Any intelligent civilization anywhere in the universe that explored the same simple equation would find the exact same shape. In the end, the Mandelbrot set is more than just a mathematical curiosity. It is a window into the deep connection between order and chaos. It teaches us that incredibly complex systems can emerge from very simple rules. This simple idea has changed our view of the universe. It encourages us to look for the hidden patterns in the world around us, from the jagged peaks of a mountain range to the intricate web of galaxies in the cosmos. Benoit Mandelbrot gave us a new language to describe our world, revealing a universe that is infinitely more complex, beautiful, and interesting than we ever imagined.